An 800-mile electric car can sound like a magic trick. After years of bold claims, many readers feel a small, stubborn doubt when solid state appears in a headline. Back in 2018, the technology was framed as almost ready, maybe even by 2020. A pandemic brought extra time, but the promises kept coming, week after week, from battery firms and automakers. Late 2025 has arrived, and mass-market, all-solid-state packs still are not on sale. Yet pilot lines, sample cells, and road tests now show which players are closest, and why 2027 keeps returning as the target year on many roadmaps. Hype fatigue. Solid-state batteries get called the next big thing because the promise list is so clean. More range comes from higher energy density. Faster charging comes from smoother ion movement and better heat control. Lower fire risk comes from removing the flammable liquid or gel used in most lithium-ion cells. Lower weight comes from packing the same energy into less volume. The core change is easy to describe. Today's cells place a liquid or gel electrolyte between an anode and a cathode, while a solid-state design replaces that liquid with a solid electrolyte. In theory, that solid layer can be thinner, safer, and allow lithium metal designs that store more energy. The hard part is the jump from lab bench to factory floor, sometimes called the Valley of Death. New materials behave well in tiny samples, then misbehave when made by the thousands. Manufacturing yield can be low, so costs explode. Interfaces between two solids can fail because microscopic gaps block ion flow. Lithium can grow needle-like dendrites that short a cell, so separators must stop them every time. Scaling from small batches to gigawatt-hour lines demands tight control, fast inspection, and stable supply chains. The result is a decade of headlines that sound final, followed by delays that sound familiar. That context matters when any company claims a production vehicle is only months away. Volkswagen's two bets. One route runs through China. In October 2025, Gotion said its all-solid-state Jinshi battery had entered pilot-scale production, and that design work had begun for a planned 2 gigawatt-hour mass production line. Gotion claims about 350 watt-hours per kilogram at the cell level, above Tesla's 4,680 reference cell, and talks about a pack range of nearly 1,000 miles, stable operation from -20 to +85 degrees Celsius, and a projected lifespan of 1 million kilometers. Its roadmap points to small-scale vehicle integration around 2027, with mass production closer to 2030. The other route runs through the United States with QuantumScape. Its concept is often described as lithium metal and anode-free. Instead of building a thick anode into the cell, the lithium metal anode forms during charging. A ceramic separator acts as the solid electrolyte and also blocks dendrite growth. QuantumScape points to a little over 300 watt-hours per kilogram, plus fast charging, such as 10 to 80% in about 15 minutes. In 2025, the company reported shipment of B1 samples of its QSE-5 cell and described installing an automated pilot line in California using a new process called Cobra. Demonstrations, including a solid-state pack used in a Ducati electric motorcycle linked to Volkswagen, suggest the partnership is moving from slides to hardware. Analysts keep circling the same milestone year, 2027. The giants, CATL and BYD. The world's biggest battery makers have the resources to turn a good idea into a real product, but their messaging has grown cautious. CATL has said it entered trial production of relatively small all-solid-state cells and has floated lab-scale numbers around 500 watt-hours per kilogram. Those figures live in prototype territory, so skepticism is healthy. CATL has worked on the topic since 2016 and reportedly has around 1,000 people focused on the problem. Even so, the company has described itself as only around technology readiness level 4, and it has warned that charging speed, cycle life, cost, yield, and manufacturing scale remain major hurdles. Its chief executive, Robin Zeng, has also said all solid-state batteries are still years away from full commercialization. Even with talent and cash, physics and factories set the pace. CATL's own target for a production-ready batch again points to 2027. BYD looks similar. A small prototype line has been reported for roughly a year, with energy density around 400 watt-hours per kilogram. BYD has also talked about a demonstration vehicle around 2027, with full commercial production nearer 2030. For both firms, the barrier is not only electrochemistry, it is the need to beat the cost and reliability of their own lithium-ion, and in BYD's case, also sodium-ion offerings. That benchmark is brutal. Still, these companies have delivered massive scale before, so their conservative tone may be the most credible clue about what the industry can truly ship. Chery's bold number. Chery has made one of the loudest claims. In November 2024, the company said a gigawatt-hour level all-solid-state battery production line was under development in Wuyuechu, in China's Anhui province. In January 2025, the first batch of engineering samples reportedly rolled off the line with real-world cell energy density around 300 watt-hours per kilogram. That level can fit a believable early product if the cells can be made reliably. Then came the eye-catching jump, a new prototype claimed at 600 watt-hours per kilogram. Chinese press reports tied that number to a possible real-world range above 800 miles, or about 1,300 kilometers. The headline is thrilling, but the gap between a lab star and a factory workhorse is huge. A 600 WHKG cell pushes limits. High energy density often means tighter layers, more reactive lithium, and more fragile interfaces. Tiny flaws in stackings, pressure, or sealing can cause rapid failure. Heat management becomes harder because more energy sits in the same space. Quality control must catch defects that are invisible to the naked eye. That is why many first-generation solid-state products aim closer to the 300-350 WHKG range, where manufacturability has a better chance. Chery's own wording suggests the 300 WHKG version is the nearer-term commercial step, while the 600 WHK version remains a development target. Even so, Chery has put a date on large-scale rollout, and the date matches the growing pattern across the industry: 2027. Semi-solid detours and Tier 2 contenders. Some of the longest range stories use a halfway approach. NIO has highlighted its ET7 sedan passing 650 miles on one charge using cells from WeLion. Two details matter. The pack was about 150 kilowatt hours, roughly 1.5 times the size of many high-end EV packs, so long range is easier. And the cells are semi-solid, not fully solid state. A small amount of gel remains inside, helping fill microscopic gaps between solid layers and boosting ion transfer at the interface. But the gel keeps extra steps that true solid state aims to avoid. Production still needs dry stages and wet filling, tougher sealing, and added checks to confirm the gel sits evenly. Semi-solid designs may act as a bridge, but they also carry some of the old complexity. Below the biggest names, several firms keep pushing. Farasis, backed by partners including Mercedes-Benz, has a pilot line producing Gen 4 pouch cells and has claimed around 323 watt-hours per kilogram. Prologium in Taiwan has been linked to a planned gigafactory in Dunkirk, France, aimed at 2027. Its superfluidized process temporarily makes a ceramic electrolyte flow during manufacturing so it can fill micro crevices, then it solidifies before the line ends. Recent prototypes have been cited around 360 watt-hours per kilogram, with a next step aiming toward about 470. These numbers show progress, but the real test remains repeatable output at scale. A likely landing zone. South Korea is building quietly too. SK On opened an all-solid-state pilot plant in September 2025, south of Seoul. The site is about 50,000 square feet, roughly 4,600 square meters, and it is designed to turn research into a repeatable process. SK On has discussed a target volumetric energy density of around 800 watt-hours per liter. Converting that to a weight-based figure depends on cell design, but it could translate to something like 280 to 300 watt-hours per kilogram in later products, with targets reaching toward 2029. That may sound less dramatic than 600 WHK headlines, yet it fits the pattern of steady, buildable gains. Across China, the United States, Europe, Japan, and South Korea, the same story keeps surfacing. First comes pilot-scale production, then come sample shipments and limited vehicle tests. Only after that do costs and yield improve enough for mass output. That is why so many roadmaps cluster around 2027 as the first year when several companies hope to prove real integration in vehicles, even if wider rollout slips closer to 2030 for many brands. The hype has burned trust, but the current signals are stronger than press releases alone. Pilot lines exist, prototypes are improving, and some partners are already putting cells into moving machines. The finish is not here, but the race is no longer imaginary. The solid-state race now looks less like one finish line and more like a chain of gates. First comes stable pilot production, then limited vehicles, then the hard grind toward mass scale. Range claims will keep popping up, but the key questions stay the same. Can the cells be built safely, cheaply, and with high yield? Can they charge fast and last for years? The most honest signals are factories, not headlines, and several are finally real. If 2027 brings the first true launches, the next years will reveal who can scale. For now, caution beats hype, and progress counts.